In the third part of the Chapter 6 lecture on momentum, I will talk about the principle of conservation of momentum and how it relates to different types of collisions between objects. Conservation of linear momentum is a principle that is applied to a system of objects. Let's first define what a system is. So let's consider a gas, which consists of molecules, of course. It is trapped inside a container of some sort. So this is the container. The walls of the container are thick enough so that they do not bend. But we want the molecules of the gas to never interact with the walls. So we will pretend that the molecules do not collide with the walls of the container. And so let's look at several molecules. And so these molecules will have different masses. Mass M1, mass M2, mass M3. And they will also be moving with different velocities. V1, V2, V3. And so these velocities are randomly directed. Inside the container, the molecules are moving in a completely random fashion. So knowing their masses and velocities, I can then assign momentum to each of those molecules. So the first molecule has momentum M1, V1. The second molecule has momentum M2, V2. The third molecule has momentum M3, V3. And so the collection of those molecules is my system. The container itself is not part of the system. Furthermore, I'm going to consider my system of 3 molecules isolated from the surroundings, meaning, as I said, the molecules do not interact with the walls. Imagine that they do not collide with the walls. The walls are thick enough so they do not bend, which means that if an external force was applied to the walls will not bend, and then that will not affect the movement of the molecules inside. So even though the molecules are contained by this container, we would consider them as being completely free to move everywhere without interaction with the container. No external forces act on the molecules. So this is an example of an isolated system in that sense. And such system can be, or an isolated system can be formed by all kinds of objects, with the only condition being no external forces act on the objects of the system. So we can have also, let's say, train cars that interact with each other on the tracks. We are going to ignore external forces such as friction. And so when these train cars interact with each other, that is a system of particles or objects that interacts with each other. Okay, so then if we have such system of objects that does not experience external forces, the total momentum of the system remains constant. That is the principle of conservation of linear momentum. Let's sketch that. So here is my system from the previous slide. The container, the 3 molecules with their momenta. And let's say that the current configuration of the system, the way the molecules are spaced right now and where the position in the container is with the directions of the velocities as shown, let's call this the initial state of the system. So after some time, because these molecules are moving around randomly, the position of the molecules will be different, and the molecules may interact with each other as they're moving inside the container, which then will result in changes in their velocities. May result, may not result. Some may change, some may not change. In general, let's assume that the velocities change. And so here is my system. After some time, the particles have moved around. They have, in general, different velocities. So the molecule with mass M1 now is here, moving in this direction with a new velocity. Let's call it V1 prime. Particle number 2 or molecule number 2 is moving in that direction with a new velocity V2 prime. Particle 3 is moving in that direction with a new velocity V3 prime. And so the momentum of each particle or each molecule now is shown as well. P1 prime is the momentum of the first particle. That is the product of its mass and velocity. The momentum of the second particle is shown, and the momentum of the third particle is shown. So in general, these momenta here are different than the momenta at the initial state. What the principle of conservation of linear momentum says is that the total momentum of the system in the initial state is equal to the total momentum of the system in the final state. So the principle of conservation of linear momentum says that the total momentum at the initial state let's call this one P sub I, is equal to the total momentum at the final state. And let's call this one P sub F. And so at the initial state, the total momentum P initial is equal to the sum of the momenta of the individual members of the system. So P1 plus P2 plus P3. And then at the final state, the total momentum PF is equal to the sum of momenta of the individual members of the system. So that's P1 prime plus P2 prime plus P3 prime. And of course, keep in mind that these can be extended for more than 3 members of the system. If the system has 100 members, then you just add the individual momenta for each member, and that is how you calculate the total momentum. And so then, from the conservation of linear momentum principle, we can say that P1 plus P2 plus P3 is equal to P1 prime plus P2 prime plus P3 prime. And so this follows from conservation of linear momentum. Well, this principle, the way that it's presented right here, can be used to solve certain types of problems involving a system of moving objects. And I will demonstrate that with an example. Here is the example. A 2-kilogram boxcar moving with 10 meters per second collides with 4 identical boxcars initially at rest. After collision, the 5 boxcars move together as one. Find the velocity of the 5 boxcar train. So, to solve this problem, I'm going to use conservation of linear momentum. Here the system is the 5 boxcars. The initial state of the system is the one boxcar moving with 10 meters per second towards the other 4 which are stationary. And then the final state of the system is all 5 boxcars moving together as one in a 5 boxcar train. So I can apply conservation of linear momentum by calculating the momentum of the system, the total momentum of the system before the collision and after the collision. So let's see what that looks like. So before collision, we have this one boxcar which has mass of 2 kilograms and it's moving with velocity v1 equal to 10 meters per second to the right. The other 4 boxcars are at rest and they all have a mass of, each of them has a mass of 2 kilograms. And the velocity v2 is 0 meters per second. Okay, so then I can calculate the total momentum of that system. P initial, which will be P1 plus P2. P1 is the momentum of the moving boxcar, so this would be M1 times V1. And P2 is the momentum of the 4 boxcars that are at rest. So that will be M2 times V2. This becomes 2 kilograms times 10 meters per second plus 8 kilograms times 0 meters per second. Or the initial momentum would be equal to 20 kilograms meters per second. Now let's look what happened after collision. So after collision, we have all the boxcars moving together as one. Each of them has, again, a mass of 2 kilograms. The velocity with which they are moving, let's call it simply v. Well, let's call it v prime, is what we are looking for. So the final momentum of the system is simply equal to the mass, let's call it m prime, times v prime. So m prime is the total mass of the 5 boxcars. So this is 10 kilograms. And then the velocity is v prime, and we want to find it. So conservation of linear momentum says that in absence of external forces, there is no friction in this problem. The total momentum before or at the initial state must be equal to the total momentum at the final state, which means that 20 kilograms meters per second must be equal to 10 kilograms times v prime. Let's set them equal to each other. So we have 20 kilograms meters per second equal to 10 kilograms times v prime. From here I can solve for v prime, and v prime is 20 kilograms meters per second divided by 10 kilograms, and that gives me that the velocity of the train after collision is 2 meters per second. So let's analyze the result. So we have a single car with mass 2 kilograms moving with 10 meters per second. It collides with the other 4, and now all of the 5 are moving together as one. So the mass of the system remains the same, but now because all particles or all members of the system are moving as one, the combined mass of all of them has to move together. So the combined mass here is 5 times larger than the mass of the moving car before collision. And we found out that the velocity of motion after collision is 5 times smaller than the velocity of the car before collision. So what happened was the mass increased 5 times, the velocity decreased 5 times compared to before the collision. Now this is a somewhat unique result because the masses of the cards were selected to be equal. However, in more general problems, the masses will be different. The objects will be moving with different velocities, and so then the solution will be a little bit more involved. However, for our purposes, this type of example is perfectly adequate to illustrate the principle of conservation of linear momentum. And so, one more time, for those types of problems, you need to calculate the total momentum at the initial state, which is simply the sum of momenta of the individual particles or objects in the system. You also need to calculate the total momentum after collision, the final total momentum, which is just the sum of momenta of the particles or objects in the system. Set the two equal to each other, and then solve for the unknown quantity. In the example that I just discussed, I used the term collision. Collisions are important events in the science of momentum and also energy. And I would like to spend a few moments explaining the types of collision possible between objects in nature. So first we have elastic collisions. Elastic collisions are collisions for which the shape of the colliding objects does not change during collision. And such objects, for example, would be billiard balls, steel metal spheres, a bowling ball hitting the bowling pins, and so on and so forth. So when elastic collisions are under consideration, think about rigid bodies and undergoing those collisions. So one more time, elastic collisions are collisions for which the shape of the colliding object doesn't change during collision. The second type of collision is the inelastic collision. Inelastic collisions are collisions for which the shape of the colliding object changes during collision. But after the collision, the shape is restored. For example, a basketball that is thrown at the wall, when it hits the wall, it's going to deform a little bit, but once it bounces off the wall, it regains its original shape. So that's an example of elastic collision. Inelastic collision, where the shape changes. And again, during an inelastic collision, the shape of the colliding objects changes during collision. So let's give the examples for the two types of collisions. So for elastic collisions, we have billiard balls colliding with each other, or steel spheres colliding with each other, or a bowling ball hitting bowling pins, or any such type of collision where the shape of the colliding objects does not change. For inelastic collisions, the shape of the objects changes during collision, and for example, example of such collision would be a ball bouncing off a wall. Now, there is a specific type of inelastic collision for which, during the collision, the colliding objects deform, change shape, and then they do not return back to the original shape. They also can get stuck together and move as one object. So those types of collisions are called completely inelastic collisions. So these are a subset of the inelastic collisions. Completely inelastic collisions. So for those collisions, again, the shape of the objects that collide changes After collision, the shape does not return to the original shape. And these objects can also get stuck together after collision. A simple example would be a piece of clay that's thrown at the wall. It hits the wall, it deforms, and gets stuck to the wall. Another example of completely inelastic collision would be the collision between those boxcars in the example that I did for you. After collision, they were all stuck together and moving as one. So that's an example of a completely inelastic collision. So completely inelastic collisions are collisions for which the shape of the colliding object does not restore after collision. Another example of a completely inelastic collision would be when cars enter car crash. After that, they remain obviously deformed, so the shape does not return back to the original shape. So that's also an example of a completely inelastic collision. So how are all these types of collisions related to the principle of conservation of momentum? Well, the principle of conservation of momentum is valid for all these types of collisions. So no matter what the collision type is, the principle of conservation of momentum applies. One more time, conservation of momentum applies for all types of collisions. And with this, I'm concluding the lecture on momentum.